Hello everyone, today I'll be introducing our work Radiance Meshes for Volumetric Reconstruction. For a set of images and their positions, we can use volumetric reconstruction to fit a glowing cloud to match our inputs. This reconstructed cloud, or radiance field, can then be viewed from new viewpoints, often giving photorealistic results. Techniques for representing radiance fields can be split into two categories, fields and sets of primitives. Then, we can either ray trace or rasterize the result. Rasterization, which is often faster, works by projecting primitives into image space before rendering, while ray tracing works with individual rays in world space. Our work, the Radiance Mesh, fills a gap in the taxonomy of radiance field techniques by introducing rasterization for fields. Radiance fields were first introduced in neural radiance fields, which used ray tracing via numerical quadrature to integrate a field, which was represented by a neural network. However, this approach was slow to render and slow to train. Then came 3D Gaussian splatting, which introduced the first radiance representation that could be rasterized. However, the speed comes at a cost. 3D GS relies on approximations that cause noticeable popping artifacts. These splats are also difficult to edit and struggle with complex camera models, like fisheye lenses. Then came Ever, the first method to produce an analytically correct way to render the primitives without any temporal artifacts using ray tracing. However, even with hardware acceleration, ray tracing for transparent surfaces is still slow. We introduced the Radiance Mesh, which is the first field that can be rasterized. Radiance meshes are fast to render, easy to edit, view consistent, and support complex cameras. The Delaunay triangulation and the Voronoi diagram are two popular types of point set tessellations, which happen to be dual to each other. The Voronoi diagram changes smoothly as the points move, while the Delaunay triangulation experiences sudden jumps. For these reasons, a previous method, radiant foam, chose to represent the field using a Voronoi diagram. However, the Voronoi diagram is composed of arbitrarily complex polyhedra, which are hard to rasterize and are not easily compatible with the existing graphics pipeline. We chose to optimize the Delaunay triangulation. If we naively attach color to the vertices, the jumps in the Delaunay triangulation cause a sudden discontinuous jump in appearance. Our solution is to query a neural field at the tetrahedron circumcenter. Now, at the exact moment of the flip, the circumcenters of the new tetrahedra are co-located with the old ones. This makes the transition continuous and allows for stable, gradient-based optimization. Our improvements stabilized optimization, allowing our method to surpass radiant foam in quality. Not only is our optimization better behaved, but the resulting radiance mesh is more flexible and composed entirely of triangles. We now describe how we rasterize a radiance mesh. We start by sorting the tetrahedra by a quantity called the power of the circumcenter with respect to the camera position. Back in 1997, Karasik et al. Proved that this gives the correct sort order for that camera position, and gives us the ability to sort all of the primitives using a single radix sort, which takes less than a millisecond on a fast GPU. We take our sorted primitives and feed them into our rasterization pipeline, which emits a triangle strip for each tetrahedron. We then attach the tetrahedron attributes to the vertices, which the fragment shader then accesses to calculate the transparency and color of each pixel. Our novel rendering technique is extremely fast. At 1080p, our method is 32% faster than 3D Gaussian splatting. Across all MIP Nerf 360 scenes, Radiance meshes define the new state-of-the-art for performance per primitive. But the real power of Radiance meshes is what they unlock. For example, we can easily support complex camera models, like this fisheye lens. We can extract a watertight surface mesh for use in any standard 3D game engine or modeling and animation software. Although our Radiance mesh is not a surface mesh, it is still compatible with many parts of the graphics ecosystem. Here, we're using position-based dynamics to interactively simulate forces on the mesh. Here is a demonstration of our web viewer. We believe that our approach represents a compelling combination of highly desirable properties for radiance field models, and we hope that this work will bring the community closer to widespread adoption of radiance field techniques for user-facing computer graphics applications. Thank you.